So initially, why do we check temporary work? So most people in the construction industry, I guess, will be aware of the Florida bridge collapse, but it highlights highlights why we're doing this presentation to start with, of why we check temporary works and why it's important. So it was, I think, 2018 this came down, but there were a number of reasons why it failed. But the important ones, with kind of respect to today, are the lack of checking. So this is from the SCOS alert and that was put out after, I think, in 2020. But I kind of highlighted that there wasn't a peer review, which is the American equivalent for Cat 3 check on the bridge in the temporary condition during construction. And also that when the cracks started to appear around the nodes, it was inspected, but it was not thought to be critical. And that was the other things that ultimately led to the collapse, and it collapsed onto a live highway. So there were a lot of ways this could have been prevented, but it's why we are talking about checking of temporary works. So back to the UK and what kind of ultimately led to BS 5975, which is the British standard on temporary work. So there's a number of failures of temporary works in the 50s, 60s, and 70s. I've only picked one of them for this presentation. So we've got Barton Viaduct. So this collapsed in 1959. It killed 2 people and injured, I think, 8 others. And there were a number of failures on this project. I think there were 3 fatal accidents. Scaffold was not designed properly, which is what ultimately led to the failure. It was observed bowing prior to the collapse, but it was left until it failed. And this ultimately led to the Bragg report. So this led to kind of industry leaders looking into how they tackled this, and it was commissioned by Sir Stephen Bragg, which it was named after. There were 27 recommendations within the report. This ultimately led to BS 5975. The recommendations kind of broadly were defined or separated into technical failure or technical improvements, procedural recommendations, and then training and competence. And this led to BS 5975 as we know it today. Bits that we're going to be discussing. So there were, of those 27 recommendations, there's kind of 5 that relate to checking, or these kind of 5 where we're going to be discussing. So number 13 was to do with the qualifications and training of the engineers carrying out the works. Number 14 was like independent checking of temporary works, especially as they were defined then novel features. Number 15 was coordination between temporary works and permanent works engineers and that kind of interface. 16 was to do to the impact of changes. So after the design's been carried out, if changes are made to the temporary works, has a design and has a check being carried out on those changes. And then 17 was the establishment of the TWC role, the temporary works coordinator on site, and their duties. So broadly why we're talking about checking. So overall, the Bragg report kind of why temporary works are checked more than permanent works is quite often a question that's discussed and asked. So temporary works, we are looking at a permanent structure in the temporary condition, and that can quite often be the critical state, as was with that Florida bridge. There's really large loads applied in temporary condition in a lot of situations. You've got large cranes, mobile plant, that kind of thing. When it comes to demolition, you're dealing with a historical structure where a lot of record drawings are often lost, damaged, or just not decipherable. Construction quite often hasn't been considered, and that leads to a construction sequence which adds risk to a project, adds risk to the operatives doing it. There are time and cost pressures to do with temporary works. Like anyone that works in the industry knows that these things are considered at the last minute quite a lot of the time, and it's always a mad rush to start looking at these designs when a contractor gets to site. And the extended supply chain in a lot of modern construction involves different kind of silos of designers not working collaboratively. And there's the grey areas in between these designs where an interface may not be designed and may lead to a dangerous structure. So onto checking of temporary work. So there's the internal checking, so the design side checking, and then the site-based. And what we're thinking about is not just does the design work, but is the brief correct? Is the information that's being used in the design, is that being correct? And does the design look correct? So when you're looking internally at what you are designing or what's being designed, does it look like it will work? And that comes with a lot of engineering experience. Check that the design or the calculations are correctly illustrated in the drawing. So the design is or the calculations prove the design works. And then when it comes down to the checking, is that information provided to the checker that they've got all the information they need to carry out the check. When you move on to the site side, when you towards the TWC, they need to be making sure that the checker is satisfied with the design, that they've got all the proper procedural kind of certificates in there. Check it's installed properly, so check that any sequence of installation is followed, the design is installed correctly as per the drawings, and that any limitations there are obeyed. So if there is a loading allowance on certain elements of the temporary works or the permanent works in a temporary condition, check that that is in place. And also, one that's always forgotten, how do you remove the temporary works? Is there a methodology for removal? I get to use Josh's favorite picture now of garbage in, garbage out. And we are doing a webinar on design briefs next month, I believe, when we get around to writing it. So the design brief is vitally important to getting a good temporary works design, and checking that design brief will produce what you are looking for in a design. Is really important for the clients and contractors. So looking at your constraints, your time scale, site investigation, construction sequence, all that should be thought about in the design brief. Checking the correct loads are provided, and questioning those loads if there's something that doesn't make sense. So tower crane loads is the ones I normally notice or kind of see a lot. Sometimes those loads don't make sense. There's been such things as typo in the loads, and that needs to be kind of questioned and queried. Then with piling rigs and SI. And then when you're doing the design, check that the output is as you expect. If you're using FEA models, they're wonderful tools, but they're only as good as the information you put in. And you need to be able to analyze if that information is correct. If that's kind of giving you an output that is making engineering sense, can you do some hand calcs to check that? Are the reactions and stresses as you expect it, and is it robust? So, and finally, has the site team reviewed what you've designed? So you've done a draft design drawing, you've sent it to the site team, things have changed on site, or you've got the wrong end of the stick. Make sure that that is reviewed by the site team to make sure it is constructible and kind of highlights any constraints that there might be on site. So finally, moving on to BS 5975 and the check categories. So for those that are new to temporary works, there are 4 check categories in BS 5975, going up from 0 up to 3, with 0 being the kind of for the simpler designs and 3 being for the most complicated. I'm not going to read this out. We're going to go through it in a bit more detail on the following slides. But these are the kind of the scope of the checks, the comments, and pretty most importantly, the independence of the checker from the designer as defined by BS 5975. So with Cat 0 and Cat 1 checks, the checker should verify that design suits the site conditions. Cat 0 checks are on kind of standard design solutions. Cat 1 checks are for simple designs. When it comes to Cat 2 and 3 checks, they should be the checker should be carrying out an independent check of the design drawings without reference to the designer's calculation, and they should be verifying that the design using only the design drawings and any supporting information, kind of input loads, SI reports, kind of site constraints. Implementation risk. So this is separate to the design check categories. It was introduced into 597/5 2019, I believe. And this is a combination of the execution risk and the consequence of failure. So it goes from very low up to high, and this dictates or suggests the control measures and the permits for a temporary works design. It's not directly correlated to the design check category, but it kind of indicates the controls that should be put in place on site to implement the temporary works. So, as a very brief example, if you've got an excavation design in an empty field, essentially the implementation risk is going to be very low, probably low. There's not, bar the excavation, there's nothing else that is going to be kind of causing a higher risk. Whereas if in the example here, you've got a excavation directly adjacent to a railway, you're moving up to medium to high risk from implementation risk. And as you can see in that commentary there on it, this is the risk, or the implementation risk can vary significantly depending on the proximity to local assets. In contrast to the temporary works design might be unchanged and require the same independent design check. So it's kind of, this doesn't affect the design check category, it affects the controls that should be in place for installing the temporary works. And on the subject of Network Rail, they have a very similar method of categorizing design checks. The only difference is where the Cat 3 checks are a separate organization in BS 5975, it's a separate legal entity under Network Rail guidance. So from CIB 003, that's the only real difference. So with CIB 003, it gives a bit more guidance on the Cat 3 check and the proposal for how independent the check should be. So they look for a design statement to be produced, which outlines the method of analysis, the program of checking, and the kind of interface with the designer and the compliance. And it notes that when novel analysis is used, checkers should establish an alternative method, and they should use an independent method for carrying out the analysis. Where that's not possible, the project engineer should agree on how the validity of the design is substantiated, so that if there's not an alternative way of carrying out that design check, that they ensure they are happy the design has been independently checked. So what does this mean? So we're going to go through some typical examples now of design checks, what designs could be checked under certain categories. This is an extensive list. It needs to be decided by the project team, depending on the risk involved. And this is for guidance only. Please don't reference this when you choose your category. But working from top to bottom, so a Cat 0, we're looking at fairly standard designs. So your trench boxes, proprietary edge protection systems, that kind of thing. Who is checking it? It's someone else within the same design team. They review the calculations, the drawings, any assumptions, and they sign a check certificate if that's part of your kind of company requirements. And any queries or any issues they have, they raise directly with the designer to close them out. I'm just going to, so that was from 5975. Network Rail have their own kind of examples here, and it gives you a bit of a different flavor of what Network Rail think, but it's kind of low-level excavations, standard scaffold design to TG20, small hoardings, that kind of thing, very kind of simple standard temporary works. Cat 1 checks, so moving up the scale of complication. So it's a different member of the design team carries out an independent check of the designer's calcs, drawings, and any other assumptions, the site constraints. They sign the check certificate, and they also raise any queries with the designer directly. So that's good for kind of simple propping and needling schemes, small excavations, formwork designs, small outrigger, small crane positions, permanent false work, other hoardings, that kind of thing. There's a fair list there. I'm not going to go through them all. Starting to get more complicated now. So a Cat 2 checks, this is where it becomes interesting. So it's the same organization, so it's within the company, but it's a different design team. The checker does not have access or should not have access to the designer's calculations. They are carrying out a check on the design drawings, the inputs, any loads and SI, and a design statement if that's part of the company requirements. They sign on to a design check certificate, and any queries should be raised formally through a DRN or similar process to kind of document any changes. And the TWC should be involved with that process, should have sight of that DRN if required. So we're starting to talk more complicated designs, demolition sequences, more interesting propping schemes, that kind of thing. The network rail examples are shown there. So kind of standard tower cranes, large mounted equipment, underpinning, façade retention schemes. So complicated but not particularly novel temporary work schemes. And on to the final one. So Cat 3 checks. This is exactly the same as a Cat 2 check. The difference is that it's a different organization. So it's not within the company. You're getting an independent company to check your design. They have access to the drawings, the inputs, and design statement, and they need to satisfy themselves through calculations that the design is satisfactory. Any queries with the designer should be raised formally through a DRN or similar process. And what we're talking here is kind of novel designs or analysis techniques for temporary works. Network rails, kind of 03 examples are kind of demolition of kind of multi-span masonry bridges, complex partial demolitions, large basements, complex or suspended tower crane bases. So you're on the more complicated side of temporary works. So this just kind of outlines with Cat 2s and Cat 3 checks, the checker should not have access to the designer's calculations. It's happened a number of times where someone's claimed to carry out a Cat 3 check and have annotated our calculations and sent them back to us. That's not a Cat 3 check. And it's important that difference is kind of noted. So just a bit of 5975 which clarifies that. So you should expect as a kind of contract client of your Cat 2 or Cat 3 check. So an additional set of calculations produced independently of the design calculations, ideally a different approach or different software used. They shouldn't be a review of the original calculations, and most importantly, they shouldn't be full of caveats. They can't just go, well, this bit works, but we've not checked this section. It should be the checker should be satisfied that the design in its kind of entirety works. They should check the actual most up-to-date design. It shouldn't be a check on something separate, and any concerns should be raised and rectified before the design check certificate is signed. As I've said before, TWC should be involved with the review process, and a formal record should be made of the discussions and changes. And just a final point here, the calculations and check calculations do not form part of the design outputs as per BS 5975. The design drawings, the check certificate, the DRA is the design output, the design statement, but not the calculations. So On completion of a design check, you will receive, or of a Cat 1, Cat 2, Cat 3, there'll be a design check certificate. This should identify what has been checked, and both the designer and the checker should be signing on to this check certificate. So they should be certifying exactly what's been checked, any limitations or any loading constraints, and signing to say they are happy. This is a very typical one where you've got kind of the drawings produced, what design standards have been used, and the category of check. And it would be signed once complete. It should kind of outline what documents and drawings have been utilised. In this case, it's the tower cranes. You've got the tower crane load, the pile capacities, probably some foundation plans. So it kind of outlines what information has been used in the design. So on to on-site checking. So the TWC, or they can delegate it to TWS, are responsible for signing off the permit for load of the temporary works. They maintain the temporary works register, and they should be ensuring that the designs and the checks have been carried out prior to loading. So if the design is not erected as per the drawing, they should be ensuring the designer is notified and the checker, and that there is agreement prior to loading that any changes to the design are satisfactory, and the check should be completed for all designs prior to it being loaded. So things to kind of, got some examples of issues noted on site. So this one's props loaded non-concentrically. You've got a U-head there that's not being rotated, and you've got significant bending in the prop head. Example of some propping where they've used whatever they've found on site to form a pin when it's been lost, which is clearly not as per the design. And this one where probably a design hasn't been undertaken. It's poured a wall against an existing garden wall that's collapsed into their neighbour's property. So examples of what happens when this isn't undertaken correctly. So I'm going to now hand over to James. He's going to talk about a Cat 3 check that he carried out recently, and then I'm going to got a final small Cat 3 check and we're going to discuss.
Yes, thanks, Dave. So yeah, the project I'm going to talk about today is the installation of a 25.5 metre wide, 1,200 ton shaft lid at Abbey Mills pumping station. Sarans completed the design works and supplied the equipment, and we were the Cat 3 checkers on the project. The project was part of the Thames Tideway scheme. So first of all, what is the Thames Tideway scheme? Currently, the London combined sewer system discharges into the river when it reaches capacity. The Thames Tideway project is essentially a large overflow relief tunnel. So instead of the overflow going into the river, it's going to overflow into this new tunnel. The route of the tunnel is shown on the screen, and starting in the west of London, the tunnel passes predominantly along the river to pick up the discharge locations through London up to Abbey Mills pumping station, and then on to Beckton sewage treatment works in the west of London, in the east. If anyone doesn't know about this scheme, I'd recommend looking into the project further. There's loads of information online on the Thames Tideway website, and also several videos on YouTube that I'd recommend for further reading. So in our involvement on the scheme, we completed the Cat 3 check on the lifting frame arrangement that was proposed by Sarans to pick up and move this massive 1,200 ton diameter with 25.5 metre diameter lid into place. This consisted of checking the lifting lugs, overall stability during the lift and during the move, checking the structural adequacy of the system, and checking the SPMTs. The installation of the lid marked the completion of the main construction stage of the project. With that in mind, with it being such a large, complex operation, it attracted quite a bit of media attention and featured on BBC News. So here we can see a drone shot of the system just before the move occurred, just to give a sense of scale. The width has been noted on the screen as 42.3 meters from the end of one side of the SPMTs to the other. So pretty massive stuff. So for our checks, the first item in the checking process was the load takedown. So the designers of the lid, the permanent works designers of the lid, provided target loads for the system. Now, I say target loads because there was a degree of uncertainty to the exact load distribution due to the size of the concrete lid, its relative stiffness, it's the slight unequal load distribution of the lid, the relative stiffness of each component in the lifting system, and the fact that we were picking up with 8 strand jacks in 8 positions. There was a reasonable chance that the loads are not the basic static calculable loads. To kind of explain this, if you imagine one of the strand jacks takes the load fractionally before another one, it's possible that there's quite a large load disparity than would normally be the case. To give this kind of context, the same load theoretically could the same jack could a strand jack could theoretically either be unloaded or have a 3,400 kilonewton load, depending on these various factors. So determining the worst credible loads was therefore pretty challenging, because in each instance you can't just take the worst credible load, because when one takes a greater load, the ones to the side of it would take a smaller load. So it was quite an interesting load takedown to start the analysis. In addition to this, we had to consider the wind loads. There was a slight incline on the site, notional horizontal loads, and acceleration and deceleration load effects to the structure had to be considered. Particularly the deceleration loads from heavy braking, because the whole system had so much weight and was bottom heavy but supported from the top. Under heavy braking, there's obviously a lot of momentum at the bottom, so there's potential for a sort of swing or a movement at the bottom, which would obviously transfer quite a high horizontal force to the top of the system, which had to be considered in our analysis. So once we were happy with the load and the load takedown, we started by checking the main lifting anchors. So the anchors look relatively straightforward on the image above, until you realise the sheer scale and loads that we are checking. So this base plate was a 1 meter square base plate, and the factored load was greater than 5,000 kilonewtons. You can see in the model actually how we took the horizontal load into account by pulling not entirely vertically on the system, so it's not a vertical. The section on the top was not quite vertical, which is interesting. So the next thing to do is to create a model of the structure that will enable us to check both the stability and the components. The model again was fairly challenging due to get to run correctly due to several factors. Firstly was the size of the lateral forces being applied and how to accurately model how these loads would traverse down the structure, which was essentially, you imagine these box girders that are the main members in the system are sort of 2.5 meters deep, 1 meter wide sections, which meant that a typical basic analysis would not cut it, because if you imagine you model the center lines of these beams as the locations of the beams, but the load is being applied maybe like 2 meters up from the beam, the center line of the beam above, 2.5, 3 meters up. So there's a lot of challenges in the analysis and how we model this structure to make sure that we got we didn't attract parasitic forces into the structure. Thirdly, was how to model the support of the SPMTs and make sure it was all working correctly. So very complex analysis model. So once we got the model running, we obviously had to make sure we knew the model was running correctly. So we completed several sense checks to ensure this was the case. So we checked the deflected shapes, and we checked shear forces and moments and how these move down the structure, and torsion as well, because there was a fair degree of torsion applied to some of these beams. And we completed hand calculations of the loads that were applied to each member to make sure that this whole system was working correctly in the analysis model. And only at this point did we start to use the model in anger and apply the correct and complex load cases. An interesting part of this check was analysing the main girders. Each beam almost acted as two beams, in that the inside and outside webs took quite different loads. So these were the sort of stiff points of the beam with where the webs were. But these are about a metre or so apart, and due to the stiffness of the beam that's loaded, caused a disparity in the loads across the beam. So it was roughly a 70-30% split on one side of the beam to another. So that was quite an interesting analysis to complete. So we then checked the components. So typically we had data sheets from the Sarans components that gave allowable bending moments and shear forces for the beams, but due to their strange stress distributions that I just spoke about, we typically ended up looking at more first principle checks. This meant that we kind of had to duplicate our analysis, because where we could check a component in proprietary, we would have to apply different load factors, because we got the allowable load versus the ultimate load when we were looking at the first principles checks. So yeah, there's interesting elements to check. So following the full analysis of the elements, we also checked how the loading was applied to the SPMTs to make sure they were within their rated capacities, which is quite an interesting check as well. Upon completion of the check, we had a couple of queries. Once completing, so we initially completed an internal review, which we always do on our works prior to going to the client with any queries. We then had a quick phone call, courtesy phone call with Sarans, the designers, who are just to say, look, we're happy with the overall package. A couple of minor items that just need clarification on. We then raised a formal DRN and had a collaborative meeting with Sarans. There was a minor update, nothing major, and then we released the Cat 3 check certificate. Following this, there was a revision to the scheme that we also had to check, which was because the initial design phase was completed quite a lot prior to the main lift. So the availability, I think, of some of the equipment had changed. So essentially, they switched out some large beams for some other large beams, in simple terms. But this change was communicated effectively from Sarans to Andon, and we completed the checking works with good communication through Sarans, and re-released the check certificate. So the SPMT move was completed in April early this year, and the Thames Tideway system is now in a testing and commissioning phase, I understand. And now we've got a brief video that shows the SPMT move in action. It's interesting, you can see the every time the system stops, you can see the slight sway on the frame due to the momentum of the large mass at the bottom of the strand jets. Okay. Right, that's it for me. I'll pass back to Dave to do another case study on the Cat 3 check that he's completed.
Thank you, James. Mine seems a little bit small now in comparison, but I'm only going to briefly cover this. I spoke about it in a previous webinar, but it fitted really well with what we're talking about today. So, and I was back in Newcastle a couple of weeks ago and saw everything finished and the glazing going in. So I thought I'd share it again. But we carried out a Cat 3 check on the facade retention at Carliol House up in Newcastle upon Tyne. I think it might have been 2 years ago when we now actually did the Cat 2 check, or Cat 3 check, sorry. But the design has now been implemented, the building constructed and come down. So I'm going to speak a little bit about it. So the project overall is part of the Pilgrim Quarter development, where they are building the new home of HMRC up in Newcastle. So the client and our client for this was Bowman and Kirkland. The permanent works designer is Cundall, and the facade retention and steelwork fabrication contractor was J&D Pierce Contracts. We did the Cat 3 checking on the facade retention scheme. We also Cat 3'd some of the tower crane foundations where they were loaded by permanent works on the scheme, and some of the other kind of more minor temporary works design work that was done on the project. So the facade retention scheme, so it was the facade of Carliol House is listed. I think it's about 6 stories high, and the initial concept for the facade retention scheme was completed by Cundall, and we were in discussion with Bowman and Kirkland about the project prior to being involved as Cat 3 checker. So we were looking at the overall project. So these are the concept drawings that were done that showed a facade retention scheme on a large concrete foundation at ground level, and then they were going to backfill one of the layers of the basement, which varied in level over the size of the site, and kind of prop the basement, build the facade retention scheme, and demolish the rest of the structure. So this is a Google image of the structure partway demolished with the facade retention scheme installed. So you can see there it's a fairly significant length of structure. The constraints on the scheme from a Cat 3 checking point of view were deflection limitations, designing it within the Syria guidance on facade retention. It's kind of a steel frame building with a masonry facade, so there's cracking of that masonry facade needed to be avoided. There were a lot of buried surfaces within the pavement, and there was a partial road closure of one lane on Market Street, but they needed to maintain a single lane access for buses at Market Street. There were, as with all temporary works, quite tight timescales on the project to get it installed to enable the demolition works, and the whole scheme was loading the basement walls where they were backfilling and then trying to put in the new permanent works. So it was a very kind of interesting project. I'm not going to go into the analysis too much on this, but we were looking at where the center of gravity of this wall was, where the kind of lateral loads come from. So you've got the wind loads, you've got the potential for out of plumb loads, and the kind of offsets, especially at the top of the structure where there was a large cornice, and how that would load the facade retention scheme. So there was a lot of kind of interesting thought into how we Cat 3 check this, building up our models as James has gone over, making sure they're working appropriately, looking at the deflection, which was the kind of the critical criteria here on this scheme, and trying to kind of make sure that was realistic for the proposed works. I've got some pictures here of it installed, so it's a fairly slender scheme overall. It's well designed. See some of the cartilage for the foundation behind the hoarding there. And from the inside, it was kind of tied back to the structure with a series of Cs. And I was back in Newcastle a few weeks ago, and I stopped by because I was interested. And the mass climbers are now up. The facade retention scheme is down, and they are kind of cleaning up the facade, installing the new glazing, and it's looking really good. And the scheme overall has been a good success. There's been various posts on LinkedIn where they've been very happy with the project. So we're just Cat 3 checkers on this. It's still a good project to be involved with. And I think that brings us to the end of the presentation today. So if you are looking to know more, Temporary Works Forum is really good. 5975 is obviously, it's been referenced a lot today. And Temporary Works Principles of Design and Construction. Would also recommend kind of keeping up to date with SCOS reports. And I believe we're doing a webinar on design briefs next month. So we will be kind of discussing a bit more on procedural control of temporary works. So
Yeah, that's exactly